Hi, I'm Chuck Sorois, Chief Security and Strategy Officer for Assurance Data. And today I'm going to talk about CPU microarchitecture and how it applies to different threats like Spectre and Meltdown. Now it's going to be a very simplified version, but it should bridge the gaps for you so you can take off from there and do your own research. And always, you're welcome to contact me at chuck@assurancedata.com for any of these questions on this type of information. So let's go over basic computing architecture. The first piece of that architecture is the hard disk, represented by this square here. On that hard disk, we have the operating system and everything we need to run on that computer. And it's just a basic list of easy to read instructions that developers programs. Then we have what's known as the BIOS. The BIOS is sort of our translation from that software to the rest of our hardware. The rest of our hardware is going to be the processor, which is the item that actually does the calculations for the computer. And it's actually millions and millions of little transistorized calculators. And then we have some memory, some random access memory, which is much faster to access than reaching down to the hard disk, which is very, very slow in operation. Now, with this architecture, the operating system loads some information into memory, and that's all done with this communication here. And you would store bits of code. So for example, the operating system would be laid out in a regular fashion every time on this RAM. And because of return-oriented programming, we could cut into that and force things to run. And so that became the first way to hack. And we did a couple things with our computing architecture to limit that. The first thing we did was we sliced the memory address space of RAM to be a kernel user space, or the upper address space, and the user space. So now, when we start talking about accessing these things, if a user program tried to access kernel space, which is usually reserved for the operating system, right? If a user tries to access this, it usually denies it and causes a reset for the CPU. Now, we started to figure out as attackers that we could launch this information as what we call gadgets, or little pieces of code, and we could use that to piece it together and make our own code. We battled that with two things. The first thing is address space layout randomization, ASLR. And in order to do ASLR, we need something in between here, right? So we have to randomize and not let everything else know the keys and how to get to this, because we could access it, right? We could force buffer overflows and try to access it and that kind of thing. So we put a little device in here called the MMU, or Memory Management Unit, and it would break everything down so that way no one could see from this layer this way, because this is how our flow went, to over here, and this would randomize, the different memory, so that way you couldn't have control over it, you couldn't figure it out. There were other ways to figure it out with buffer overflows and things like that. So what happened was you could load data in here and run it as an instruction. So what we did was we broke the memory into two different parts, into instruction memory, right? So we break it down into instruction and data. And the way we did that was we added a bit onto these pages of memory called an NX bit, or no execute, for data. So that says, when you see this, do not execute it. And that's called data execution prevention. So that happened a while ago in computing. And then in about the mid-90s or so, we had CPUs that were so fast that the distance from this CPU to RAM meant that we were sitting there for hundreds and hundreds of clock cycles waiting for data to come back or instructions to come back because of the distance of copper, essentially, the copper or gold wire or gold connections. It would take the electricity actually time in nanoseconds. You know, the distance light travels is really not all that far, especially when it's not really traveling the speed of light because it's through copper or gold. So what we had to do, we had to move some of this memory onto the CPU. We kept RAM, of course, but we moved some of this memory, and we have local caching or L2 or L1, L2, L3 caching. Let's go through that real quick. So in today's computing architectures, we may have a few different cores, and we'll do a 4-core processor here. So this would be core 1, core 2, core 3, and core 4. Now they'll be on the same wafer, the same piece of wafer that so they don't have to talk very far. They're not like separated by a socket and then electrical connections and then another socket. That would be multiple CPUs. This is multiple cores on a single CPU, and the reason we do this is so they can talk together very fast and work together. Now, if we were to reach out from here to RAM, these things would be waiting all day for their memory and instructions. So we put some RAM essentially in here and called it L1, right against the core itself. We do that for all the cores, and they're all L1 cache or level 1 cache. Problem with that is while this is waiting for its fetching, and it can fetch, but it can't share the memory unless it goes down here to RAM, right? So if this core is working on something and this core wants to help it, then it'll have to reach out to RAM. It takes way too long. So these cores have to share some RAM too. So these two cores will share L2 cache, and these two cores will share L2 cache. And if I want them all to work together, I'll have a shared L3 cache. Now the way it works when I try to access data or memory, when I have an instruction that says, hey, go start to process the stack, and we'll talk about the stack in a minute. And I've created a little bit of a stack over here. Let's say core 1's working on a stack. It's first going to look for its instructions in L1 or its data in L1, and if it can't find it, it's going to look in L2. And if it can't find it in L2, it's going to look in L3. And if it doesn't find it in L3, it's going to look in RAM. If it doesn't find it in RAM, it's going to find it in memory. Now that process, to go through all that, we can measure it. And we can measure it as a watching process. So that allows us to do things like predict where or tell where this information resides if we look at the predictive functions of these cores. So let's talk about that really quickly. So let's say we're processing this stack with this core, and these other cores are not working on anything. They have nothing to do. They've already done whatever. They've done their multitasking part of their programs, and this CPU is just processing this one piece of stack. So C1 is processing this, and it takes time. It's got to run the calculations to process this stack, and then it's got to retrieve information from wherever it may find it in memory, and then it's got to wait hundreds of clock cycles. So while it's waiting, core 2, core 3, and core 4 will start to pre-process the different branches of these decisions. So the result of this processing is going to yield one of two options at the end of it. So when the program gets to this point, it's going to say, I've calculated the answer and I need to go either down this path or down this path. Now, core 2 will process both of these paths, so that way it already has these answers. And now let's say core 1 processes this stack and figures out that this is the path to take. Then this is cleared from cache and this path is used, that memory space is recovered. Now, also at this point of calculation, maybe C3, while it's calculating these two branches, C3 could be calculating these two, and C4 could be calculating these two. And it's doing a speculative execution and branch prediction. So speculative execution is actually executing these ahead of time. Branch prediction is based on a translation look-aside buffer and a BTB, or branch target buffer, and those stats are used to predetermine which path is most likely, which one of these code snippets is used most often, so it keeps the stats. Now, you can cause this, you can fake this option here many times and drive up the stats here, so that way, even though this is the wrong answer, it will more likely be chosen because you've driven up the statistics, and statistically it'll try that and pre-execute that path much further. Because, right, if very commonly in our applications we're going down this path, then why pre-calculate when we only have 4 cores to calculate 4 things? We won't calculate these if they're not commonly used. We might pre-calculate the first leg, and that's what these squiggles mean. It means speculative execution or branch prediction. So you would predict the path that's most commonly used. So if this is core 1 working on this, we have core 2, actually it's shared memory space, so it'd actually be core 3 because it's going to share L2 cache, the closest cache, and then core 2 might be doing this one, and core 4 might be doing this one. Now, you could have core 4 working on one of these guys over here, but because statistically this path is not chosen, this branch isn't predicted because it wasn't used in the past. You know, it keeps these stats. Now, you can drive up this branch prediction with fake hits to that memory call, even from the user space as a user. So you can do that, and these cores, instead of processing these ones that are most likely, will pre-process here a path that it's not supposed to. And by the time, if you flush all this cache and you make it reach way out into the disk to get these answers, it's going to take thousands of clock cycles. And you'll be able to go so far down this path and make this thing do whatever you want, you can actually start to read the information the way it works. And that's how Spectre works, or the Spectre exploit. Now, Meltdown works a little bit differently, where you can actually, down this normalized path, as a user, you can request some of the stack or a memory space, a memory location. It'll actually cause the CPU to reset, and it will actually reveal a byte of information from kernel land, which you're never supposed to see. And if you do that millions of times a second, which is how CPUs operate, then you're actually going to get the small information that resides in either RAM or on these caches. It's more likely going to be in these caches. So the servers are more susceptible than like a single CPU to be able to pull this off. So the more advanced predictive function you have, the more likely you can do this type of cache measurement side channel leak. So it's important to understand how these architectures work. So I'll step through it one more time. Hard disk holds the operating system. The operating system usually works in kernel mode and has access to kernel mode memory space, whether it's in RAM or in these caches. So these L1, L2, and L3 caches are built much like our early RAM, with higher memory space being reserved for kernel and lower memory space for user. And then additional randomization is added by the MMU, or our memory management unit, called address space layout randomization. So you can't you can't know the location of memory and call for it and force these sort of branch predictions. However, if you flush the memory and you make this and you make this process reach way out into disk or into RAM to get its answers, it can take thousands of clock cycles for the answers to happen here. And by that time, if you've done some cache manipulation, some cache training in the TLB or the translation look-aside buffer or the branch target buffer, you can drive up the stats and force your process stack to go down a path it should never go down. And you can actually control what this thing is going to run. And that's called the Spectre exploit. Now, in that process, if I request kernel memory and I'm a user, it's going to create a reset in this path, and I'll be able to leak through a side channel some of my kernel level information. Now, it's only going to leak 1 bit, but there's a limited number of bits in this cache. They're very small, so you'll be able to leak the entire contents of this cache, flush it, retrieve new cache by regular system calls from the instruction set architecture that lives in the BIOS, and you can control and manipulate these things. Now, it's important to understand that with Spectre and Meltdown, you have to patch the operating system, because the operating system, through the instruction set architecture, uses these system calls specifically for this processor. So you have to, in order to fix Spectre Meltdown, you must patch the OS as well as the firmware to tell it how to manage this process a little bit differently. And one of the ways that this is done, instead of using address space layout randomization, or ASLR, we use kernel page table isolation, or KPTI, which is pretty new. Now, you should also know that this architecture is not new. This covers CPU architectures from around the mid-90s until now. And this is not a new exploit. None of this caching or branch prediction exploit is new. It's just recently released. So in 1995, the NSA released an article that basically talked about the dangers of this. I'm sure if they're very smart people at the NSA, they may have all this time had this knowledge and maybe watching everything we do. I can't speculate, but it's just a thought. Also, at least 50 different researchers between 1995 and now have released articles at public forums like Black Hat, and different colleges have taken and leaked encryption keys out of here, private keys, in order to take over systems or read private information in under 5 minutes, most of them claim. And that was done around the 2002, 2003 timeframe, and then a couple times between then and now. With the most recent Spectre and Meltdown, Spectre is due to the speculative prediction of these, where you can force cache hits and cause this to go down a branch that it never should have gone down. And you can run your code effectively, and by the time the system comes back and retrieves and figures out that it was supposed to go down this other path, it already went down your path. You've already trained the statistics to use your path more often, and it'll just continue down whatever path you've told it to go down. And that's a very dangerous thing. So there's programs that do JIT processing, or just-in-time compiling. And what they do, like Java, will have direct interaction with the ISA layer and be able to do these things very easily and take over their shell environment. So one of the Spectre exploits released with sample code is actually a Java program, and that's very dangerous because that allows someone to run that Java code on their website. And if you were to go to that website, they would be easily able to take over that browser session from that leaked data, and with slight modification can take over the entire session. So a little bit of my own opinion about the Spectre and Meltdown vulnerabilities. I've seen where researchers said the sky's not falling, and I sort of agree with that. And some people say that it's not packaged or with an exploit that can be delivered. Well, I'm sorry, that's wrong, because we have JavaScript examples in the wild right now that were delivered as part of the release of the write-ups of Spectre and Meltdown. They both have example code that you can download and try, and many people have. So if we're downloading and trying it, the bad guys are also. And you should know that governments and nation states probably did not ignore this research, probably did not ignore the article from the NSA in 1995, probably did not ignore all the researchers in 2002, 2003, 2013, 2010, 2008. All these documents were released talking about this and how to steal encryption keys out of these caches, how to do all this. But now it's all packaged together into an explicit series of threats. And how do we deal with this? We patch them both, and we watch for anomalies. We watch for erratic system behavior where we see false cache training. We see interactions where this CPU is reaching way out down to disk when it should not be. So we have to keep track of these different types of stats to make sure that someone isn't pumping our stats into these TLBs and BTBs inside the L1, L2, and L3 caches. So this is a very, very simplified overview of how this works. There's a lot going on here, and if you have any questions or you need help with your environment, figuring out how to solve these problems for your switching gear, right? Everything's susceptible. Your watch has a RISC processor. You can take that over. Any one of your phones, any one of your tablets, your car, any IoT that's smart enough to do anything valuable, all of your laptops, Mac, Windows, Linux, very susceptible, and there are no 100% lockdown systems that aren't vulnerable to some form of this. Now, I'm sure there are many forms that we do not know about. There's these publicly released versions called Spectre and Meltdown, but we could potentially see more in the future. I'm sure we will. It's not going anywhere, and it's very hard to patch now. So we need to start looking at what I call perfect security, which is probably something formerly close to defense in depth, where you're watching system behavior and anomalies, where you need real security folks to actually look at your system and make sure things are going the way they're supposed to. So systems monitoring at the CPU and application stack level versus what's going on your network, how is stuff coming in and being exfiltrated, and patching the OS as well as patching the firmware for the CPU and the MMU to something like KPTI or some other technologies that may be coming out. Again, some warnings about these patches. If you patch the OS and not the processor, they won't know how to talk in this ISA architecture, and you'll get a blue screen. In this ISA architecture is also where AV and anti-malware play. They all, in this kernel level memory at ring 0, a lot of them will play there. A lot of them will play in the hardware level or ring 1. So antiviruses can also cause this to blue screen, right? Because they're monitoring this, and if they're not handling the system calls or CPU calls correctly, then we'll get blue screens. So be very careful when patching. Make sure you do your homework, and if you have any questions, please reach out to me. I'm Chuck at AssuranceData.com. Thank you.